All right, so we are on to 3.6, almost finishing up chapter 3 here. We're going to be talking about theorems, learning theorems about roots of polynomials. So solutions to polynomials, we're going to learn 2 theorems. The first is called the rational root theorem, okay? And we're going to apply that to this problem here. So this problem is asking us if p of x equals 8x to the 5th power minus 32x to the 4th plus x squared minus 4. It's asking us is 4 a possible solution to when the whole polynomial equals 0. So let's check that out. Let me get a different colored pen here. And the way we're going to figure that out is we're going to use the rational root theorem. So the rational root theorem is not exactly quick. It kind of takes some time, but it's a quick way to check if it's a possible solution, right? Because it gives you the list of all possible solutions. So it says all possible rational roots can be found by evaluating p over q, where p are all the factors of the constant term, so in our case here, negative 4, and then over q, which are the factors of the leading coefficient term, which in our case is 8. Sorry, I'm looking at a different problem. I was like, these don't match what I have. So let's go ahead and see if 4 is a possible solution. So let's write all the possible values of p here, factors of the constant term. So p are going to be factors, pen's almost dead, factors of minus 4. So what are the factors of minus 4? We have plus or minus 1, plus or minus 4, plus or minus 2. I think that's it, right? Okay, and then q, those are going to be the factors of the constant term, or sorry, the leading coefficient term, which our leading coefficient is 8. So factors of positive 8, that will give us plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Those are all the factors of 8. So what are our possible zeros? Well, that's going to be p over q. So we're going to make a list of our p's over q's. So we have, I'm just going to start with my 1 and put them over everything. So this is how I do it. I do plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 2, plus or minus 1 over plus or minus 4, plus or minus 1 over plus or minus 8, right? So I basically took my first p and put it over all of the q's. Then I go to my next number, which is plus or minus 4 over plus or minus 1, plus or minus 4 over plus or minus 2, plus or minus 4 over plus or minus 4, and then plus or minus 4 over the last one, which is plus or minus 8. So I'm going to do 3 rows of this because I have 3 possible numerators. So then my last one is plus or minus 2 over plus or minus 1, plus or minus 2 over plus or minus 2, plus or minus 2 over plus or minus 4, and then plus or minus 2 over plus or minus 8. So you may have been noticing that we're writing the same number. In some cases, they're just equivalent fractions. So if you were working through and you noticed they were equivalent, you could have not written them, right? So because you only need the unique p's over q's, but I just wrote them all so you could see. And then I'm going to go through and find the unique ones. So 1, 1 over 2, 1 over 4, and 1 over 8, all positive and negatives. I look here, 4 over 1, that's a unique one. I haven't had that yet, but 4 over 2, that's 2. I haven't had that yet. 1 I already had, and 1/2 I already have. 2 I already have. 1 I already have, 1/2, and 1/4. So really, there are only these 6 unique p's over q's, right? So the question said, is 4 a possible solution? Well, is it in this list? Positive 4? Yeah, it's right here. So yes, 4 is a possible solution to p of x according to the rational root theorem. Okay, so they're not asking us, is it a solution? It's a possible solution, because these are the list of possible solutions. You actually have to test them to see if it is a solution. But we don't have to do that here. We'll do that on the next one. All right. So the next theorem we're going to learn about is the fundamental theorem of algebra, a big one, right? It's fundamental. This one is about knowing how many roots a polynomial has. So in this case, it says if p of x is a polynomial of n degree and n is greater than or equal to 1, then p of x equals 0 has exactly n solutions. So if it has, it's a polynomial of 4th degree, we expect it to have 4 solutions. If it's a polynomial of 7 degrees, we expect it to have 7 solutions. One thing to note is that a factor of multiplicity, remember when a 0 shows up more than once, so if the multiplicity is m, that 0 counts m times. So for example, x minus 3 to the 4th power has this multiplicity of 3. The 0 repeats 4 times, right? X equals 3. That is considered to have 4 solutions, each equal to 3. So that's something to take into account. You still count those. So we're going to work on this one. And we're going to find all the possible zeros using the fundamental theorem of algebra, using the rational root theorem. Let's find all zeros to this polynomial. So let's list the possible zeros. Okay, so p's, my p's are going to be, remember they're going to be the factors of the constant term. So our constant term here is -2. So our p's are going to be plus or minus 1 and plus or minus 2. And then q is going to be factors of the coefficient, which is plus or minus 1 and plus or minus 3. So now this is where the rational root theorem is actually helpful, because we don't have this giant list of p's and q's. It's pretty small, right? So if we are to write our possible roots, we could have plus or minus 1 over 1, which is 1. And then you'd have plus or minus 1 over 3. And then we'd have plus or minus 2. And then plus or minus 2 over 3. So those are our lists of 1, 2, 3, 4, but positive, negative, so 8 possible zeros. So we know, let's use the fundamental theorem of algebra, because since n equals 4, p of x equals 0 has 4 solutions. So we need to find 4 solutions, and those 4 will come from this list. So what you can do is, when you have your list of possible zeros, this thing is too much to factor, I can just choose one to see if it isn't 0. So let's actually test it, okay? So if we try x equals -1, right? And I'm going to try one and sometimes your test doesn't work and you can rule it out, and sometimes your test does work and you know it's a 0. So if x equals -1, remember that means that if we factored it, it would actually be this. Factoring out x plus 1, or x equals -1 when you set it into 0. So let's see if that's a solution, which means since it's just x plus 1, I can use synthetic division instead of long division. It's a little quicker, so I'm just writing down the coefficients of the polynomial. I'm going to perform my synthetic division. Step 1, bring down the 3. 3 times -1 is -3. 4 plus -3 is 1. 1 times -1 is -1. 2 minus 1 is 1. 1 times -1 is -1. -1 minus -1 is -2. -2 times -1 is 2. And that comes out to be 0. So there is no remainder. Therefore, it is a solution. So yes, it's a solution. So remember that you can label it like this. I still always have to do this because it helps me keep track. So what I've just factored out, I've factored out an x plus 1, and I know that what's left over is this right here. 3x cubed plus x squared plus x minus 2. So this polynomial is now equivalent to this. Okay, so we have 1, 0. Let's find another 0. So let's take this and let's just pick another one. Let's try a fraction. Let's try positive 2/3. Okay, so I'm going to take this part, this what's left over, right? We've already factored this out, and see if I can factor out x equals 2/3. So I'm going to write that here. Let's try x equals 2/3, which means we're trying to factor out this. Right? Okay. So that means I can do synthetic division again. 2/3 is going to go here. And then now I'm just going to write the coefficients of what was here. A 3, a 1, a 1, and a -2. 3, 1, 1, -2. Okay, so bring down that 3. 3 times 2/3 is 2. We got rid of that fraction. That's nice. 1 plus 2 is 3. 3 times 2/3 is 2. 1 plus 2 is 3. 3 times 2/3 is 2. That's 0. Yes, we found another 0. And like I said, sometimes this won't work, but then you know you to go and try another one. So this is your constant, this is your x term, this is your x squared term. So what we have now is we have x plus 1 from before. We factored that out. We've also factored out x minus 2/3. And what do we have left? We're left with 3x squared plus 3x plus 3. Now I know I can factor this here, right? I can take that 3 out at least. So I'm going to take the 3 to the front and write x plus 1, x minus 2/3. And then since I've factored out the 3 to the front here, what's left is x squared plus x plus 1. Okay, now I have 2 solutions. I need to get my other 2 solutions from here, and I'm just going to use the quadratic formula to do that. Okay, so negative b, negative 1, plus or minus b squared, well that's 1, minus 4 times a, that's 1, times c, that's 1, all over 2 times 1. Okay, so now let's just figure this out. We have negative 1 plus or minus, what's left in here? 1 minus 4, that's minus 3 over 2. So here are my 2 solutions, right? And so that becomes what? That's negative 1 plus, I can take out an I times 3 over 2. And then I also have negative 1 plus I times root 3 over 2. So now I have all of my 4 roots. Since this was a polynomial to n degree, my 4 roots are x equals minus 1, x equals 2/3, x equals negative 1 plus I root 3 over 2, and x equals negative 1 minus I root 3 over 2. All right, so these solutions to your polynomials, finding those zeros gets lengthier now that you guys can find roots with imaginary numbers, and now that you can use these 2 theorems and division to figure them all out. All right, I'll see you next time. Bye.